Welcome to a new frontier in artificial intelligence, the integration of cosmological self-equilibrium (CSE) and the cosmological equilibrium constant (CEC) into AI architectures. In this video, we'll explore how these principles, inspired by the balance of forces in the universe, can be embedded into the very core of AI systems. At the end, you'll understand how equilibrium isn't just a physical law, it's a powerful design principle for building adaptive, robust, and ethically aligned AI. Let's begin by setting the stage for why balance matters in intelligent systems and how CSE and CEC provide a universal language for regulating information flow and feedback. Cosmological self-equilibrium, or CSE, is a principle drawn from the observation that systems, from quantum particles to galaxies, maintain their stability through internal feedback loops. These loops balance expansive forces like exploration and novelty with integrative forces such as structure and coherence. In AI, this means balancing the drive to discover new patterns with the need to maintain consistency and reliability. CSC provides a framework for adaptive feedback, helping AI systems self-correct and evolve, much like natural systems do. Cosmological Equilibrium Constant, or CEC, is a universal constraint that states, for a system to remain stable, the ratio of opposing forces should tend toward unity. In mathematical terms, that means the expansive force divided by the integrative force approaches 1. In AI, CEC ensures that the system doesn't become too chaotic or too rigid. It's about keeping exploration and exploitation, prediction and reconstruction, or entropy and structure in perfect balance. This simple ratio guides the system toward optimal performance and resilience. For introducing CSE and CEC, let's look at how standard transformer models handle attention. In these models, attention is calculated using query key and value vectors, with a softmax function determining the importance of each token. While effective at prioritizing relevant information, this approach lacks explicit mechanisms for systemic balance or adaptive feedback. The result is a static weighting that can sometimes favor certain patterns too heavily, leading to issues like overfitting or semantic drift in long sequences. To address these limitations, the CSE-CEC enhanced attention mechanism introduces two new components, the expansion score and the integration score. The expansion score captures novelty and entropy, while the integration score measures redundancy and certainty. By incorporating the ratio of these scores into the attention calculation, and enforcing a metaloss that drives this ratio toward 1, the model learns to balance creative exploration with structural coherence. This dynamic adjustment leads to more robust and adaptive information processing. In practice, the CSE-CEC mechanism encourages the model to explore new possibilities while maintaining a coherent structure. This means that during training, the AI is penalized if it becomes too focused on novelty or too reliant on familiar patterns. The result is a system that can generate responses that are both creative and logically consistent, adapting to new information without losing its grounding. This balance is crucial for applications like emotionally aware text generation and multilingual attention transfer. One powerful application of CSE and CEC in AI is emotionally aware text generation. By balancing empathy with emotional clarity, the model can produce responses that resonate with users on a deeper level. For example, it can recognize subtle cues in language and adjust its output to reflect both the emotional tone and the factual content. This leads to more meaningful and supportive interactions, especially in sensitive contexts like mental health or customer support. CSE and CEC also enhance multilingual attention transfer. When translating or transferring meaning across languages, it's vital to preserve both the original intent and the grammatical structure. The equilibrium principles ensure that the model doesn't overemphasize one language's patterns at the expense of another's. This results in translations that are not only accurate but also culturally and contextually appropriate, bridging gaps between diverse linguistic systems. Maintaining narrative coherence in long sequences is another area where CSE and CEC shine. Standard models often struggle with semantic drift, where the meaning of a story or conversation gradually shifts off topic. By enforcing equilibrium, the model keeps the narrative focused and consistent, even over extended interactions. This is particularly valuable for applications like storytelling, dialogue systems, and educational content generation. Integrating CSE and CEC into the training regime involves adding auxiliary loss functions that penalize imbalance. The total loss combines the original objective with penalties for deviations from equilibrium. This approach encourages the model to self-regulate, learning not just from data but from the ongoing balance between entropy and structure. Over time, the AI becomes more resilient to perturbations and better aligned with ethical goals. By maintaining CSE and CEC constraints internally, AI systems avoid common pitfalls like overfitting or undergeneralizing. They can sustain coherent dialogue across dynamic topics, generate responses that balance creativity with logic, and adapt to changing environments. Most importantly, this approach lays the groundwork for ethically aligned artificial general intelligence, systems that pursue goals in a balanced, self-stabilizing manner. While promising, integrating CSE and CEC into AI is not without challenges. Defining entropy and integration metrics at runtime can be complex, and the additional computations increase training time and resource requirements. Rigorous testing is needed to ensure ethical alignment and robustness, especially in open-ended or high-stakes scenarios. Future research will explore hardware implementations, self-regulating agents in complex environments, and formal unification with thermodynamic and quantum computing frameworks. Let's compare standard transformer attention with the CSE-CEC enhanced version. In the traditional model, attention weights are based on token relevance, often leading to a bias toward recent or prominent tokens. This can limit the model's ability to capture broader context or emotional nuance. By contrast, the CSE-CEC approach dynamically balances expansive and integrative forces, resulting in richer, more creative, and emotionally resonant output. Consider the sentence, "She stood alone in the fatting twilight, the wind whispering secrets only the trees could." A standard model predicts the next word is here literal and expected. With CSE-CEC, the model suggests remember, evoking personification and emotional depth. This subtle shift demonstrates how equilibrium principles can transform AI-generated language from mundane to poetic, capturing both context and feeling. Now take the sentence. The researcher observed that the behavior of particles changed when the temperature dropped suddenly. Standard attention predicts below, sticking to surface-level physical descriptions. With CSE-CEC, the model predicts triggering, suggesting causal dynamic effects. This approach not only enriches the narrative but also aligns more closely with how humans understand cause and progression in scientific reasoning. CSE and CEC principles extend beyond text to multimodal transformer models that process text, images, audio, and video. Here, equilibrium ensures that no single modality dominates. For example, in a vision language model, the ratio of visual to textual contributions is kept near 1, resulting in balanced, contextually rich outputs. This approach improves alignment across modalities, reduces hallucination, and enables emotionally aware storytelling. Imagine an input combining a sad face emoji and the text, "I'm fine." A standard model might miss the contradiction, interpreting the sentiment as positive. A CSE-aware model, however, balances the visual and textual cues, recognizing the underlying sadness. This leads to more accurate and nuanced sentiment classification, reflecting a deeper understanding of human communication. Integrating CSE and CEC into AI can be done at different levels. Shallow integration involves post-training adjustments, like calibrating attention weights at inference. Moderate integration requires fine-tuning with custom objectives, adding auxiliary loss functions to encourage equilibrium. Deep integration embeds CSE-CEC directly into the model architecture and training dynamics, sometimes requiring retraining from scratch. Each level offers a trade-off between ease of implementation and depth of systemic balance. To summarize, shallow integration allows for quick adoption of equilibrium principles without retraining, while moderate and deep integration offer more profound systemic benefits at the cost of increased complexity. The choice depends on the application's needs, available resources, and desired level of balance and adaptivity in the AI system. When embedding predictive architectures, JEPA can also benefit from CSE and CEC. By adding a regularization term to the loss function that penalizes deviations from equilibrium, JEPA models learn to balance novelty and redundancy in both image and text prediction tasks. This leads to more adaptive, context-aware outputs and moves representation learning closer to the ideals of AGI. Consider a JEPA model tasked with completing a masked image of a snowy mountain. Without CSE-CEC, the model might overfit to common textures, producing repetitive, unrealistic snow. With equilibrium principles, the output preserves natural variation while maintaining structural coherence. This balance results in more realistic and diverse image completions. For text prediction, imagine the phrase, "The ancient scroll revealed that changed history." Without CSE-CEC, the model predicts secret, a generic, high-probability word. With equilibrium, it suggests hidden equation, balancing surprise and contextual fit. This approach yields outputs that are both meaningful and specific, enhancing the model's utility in creative and analytical tasks. In a multimodal sentiment inference task, a JEPA model receives an image of a person smiling faintly with a tear in their eye, and the text, "I'm really fine, don't worry." Without CSE-CEC, the model may detect only positive sentiment, missing the visual cue. With equilibrium, it recognizes mixed or masked sadness, providing a more nuanced and accurate emotional interpretation. Neuromorphic computing, which mimics biological neural networks, can also leverage CSE and CEC. These principles introduce feedback-driven balance between excitatory and inhibitory signals, plasticity and stability, and exploration and exploitation. By simulating local feedback loops in hardware, neuromorphic systems achieve adaptive resilience, energy efficiency, and biological plausibility, key ingredients for AGI. Neuromorphic chip running a CSE-CEC enhanced spiking neural network can reduce overactivity, balance firing rates, and self-adjust learning rates in real time. This leads to adaptive resilience under varying inputs, optimal energy use, and a closer resemblance to real cortical dynamics. Such systems are not only efficient but also capable of supporting general-purpose intelligence. The nanoscale, CSE and CEC provide a framework for autonomous, self-regulating nanobots. By balancing expansive actions like movement and sensing with integrative feedback, nanobots can adapt to dynamic environments such as the human body. CEC ensures that energy use and response intensity remain optimal, preventing overreaction or underperformance. For example, a drug delivery nanobot uses CSE to regulate dosage based on chemical imbalances, and CEC to maintain the ideal ratio between action and feedback. This approach ensures precision, safety, and efficiency, enabling scalable, decentralized swarm logic. By embedding equilibrium principles, nanotech becomes not just smart but self-aware and adaptive. Knowledge hypergraphs, which connect multiple entities and relationships in complex networks, benefit from CSE and CEC by maintaining semantic balance and adaptive reasoning. Expansive edges introduce novel concepts, while integrative edges reinforce coherence. The goal is a self-correcting network that absorbs novelty without losing structure. CEC can be defined at various levels in a hypergraph: node-level outgoing versus incoming links, edge-level contextual entropy versus semantic redundancy, and subgraph-level novel connections versus redundant overlap. By prioritizing equilibrium across these metrics, the system encourages innovation without chaos and maintains cognitive alignment with human reasoning. In a query like patient shows symptoms of fatigue, insomnia, and brain fog, a standard model might focus only on biological causes. With CSE-CEC, the hypergraph output links to lifestyle, circadian rhythm, and environmental factors, providing broader and more contextually relevant insights. This approach supports richer, more holistic reasoning in complex domains. And asked to explain the causes of World War I, a standard hypergraph might list events in a rigid sequence. With CSE-CEC, the model connects nationalism, Balkan tensions, and alliance triggers, offering a richer, more interconnected understanding. This helps students explore not just what happened but why and how causes interrelate. For a query like find emerging research trends in quantum computing, a standard model may focus on popular topics. With CSE-CEC, the hypergraph output combines current knowledge with forward-looking ideas such as quantum error correction and neuromorphic integration. This approach maps the field in a more exploratory yet coherent way. In optimizing sustainable transportation for a smart city, a standard model might focus on infrastructure. With CSE-CEC, the output balances physical, social, and environmental constraints, integrating user behavior, weather, and renewable energy. This leads to robust, context-sensitive urban solutions. Neurosymbolic AI combines neural networks with symbolic logic systems. CSE and CEC bring harmony between statistical learning and structured reasoning. When neural components dominate, CSE raises the weight of symbolic consistency. When symbolic logic is too rigid, CSE increases neural flexibility. CEC-aware loss functions ensure the system balances diversity and logical consistency. In a question-answering system, a standard model may generate fluent but semantically incorrect answers. With CSE-CEC, the neural module suggests diverse candidates while the symbolic module validates logical consistency. The final output respects both contextual diversity and factual correctness, maintaining the CEC ratio near 1. Convolutional neural networks (CNNs) and recurrent neural networks (RNNs) also benefit from equilibrium principles. In CNNs, CSE balances feature diversity and semantic coherence, preventing overfitting to common patterns. In RNNs, CSE balances forward expansion and backward integration, reducing forgetting and promoting context-aware sequence prediction. CSE and CEC can be implemented at the architectural level, with dual-branch networks for expansion and integration, or at the training level with equilibrium-based loss functions. Regularization techniques like entropy-based dropout and attention weight adjustment further reinforce balance. These methods promote energy-efficient adaptive learning, especially for on-device AI. Mixture of experts (MOE) models route inputs to specialized subnetworks. CSE ensures a balance between exploratory and integrative experts, while CEC maintains a near-equal ratio of expansion to integration and expert activations. This prevents expert collapse or redundancy and supports scalable, creative, yet consistent outputs. Large concept models, LCMs, are designed to reason over abstract, symbolic, and interconnected knowledge. CSE enforces equilibrium between expansive and integrative cognitive dynamics, while CEC governs the ratio of novel connections to semantic validation. This balance supports nuanced understanding and scalable knowledge integration across logic, language, and vision. In scientific discovery, CSE enables the model to explore unconventional hypotheses, while CEC ensures outputs remain consistent with known laws. For example, when asked about gravity and thermodynamic entropy, the model generates speculative ideas but aligns them with established equations, balancing creativity and factual grounding. For moral reasoning, CSE applies abstract principles like fairness, while CEC aligns decisions with contextual norms and human feedback. This ensures that ethical justifications and situational coherence are balanced, supporting trustworthy and transparent AI decision-making. In processing multimodal inputs such as text and images, LCMs use CSE-CEC to balance visual richness with semantic grounding. For instance, when asked to show how freedom is represented in art, the system connects abstract ideas to historical visual styles while maintaining conceptual focus. Embedding CSE and CEC at the architectural level ensures that models neither overfit nor drift into speculation. This supports cognitive balance, conceptual depth, and alignment with AGI principles. Transparent reasoning pathways and internal checks make the models more trustworthy and scalable. Hybrid systems that combine language models with structured common-sense knowledge graphs, like ConceptNet, benefit from CSE-CEC. These models can perform analogical reasoning and multi-step inference, balancing expansive exploration with integrative validation for more accurate and insightful outputs. For analogical reasoning such as if democracy is to government, what is oxygen to, the model uses CSE to explore associations and CEC to align with structural relations. The output, cells, reflects a balanced, contextually grounded analogy, demonstrating the power of equilibrium in conceptual understanding.